So here you are. Can you compute anything in this frigging theory? You know, because all the other courses take semesters and etc. So for that reason, I like the very simple theory, which is called zero-dimensional field theory. So this is the simplest possible thing you can do, and you can actually do it by hand. I'm giving you problems, and maybe you don't understand what you're doing. Zero-dimensional field theory. So whenever somebody says, you know, I have 270 values of the field phi, I say, that's too complicated. Let me just have one. So I forget this index. Just one. When somebody says to go from here to there, you know, I have to do a real calculation, Fourier space, k square plus n mu square, you know, some integral something. I say, this is a little bit too hard. Let me just say propagator just one. You know, nothing happened. There are no neighbors, no derivatives, nothing. When somebody says, I will now wander around and then I'll spew off a child just like me, I'll clone myself, you say, well, you know, when I'm fishing, I care about how many coupling constants I have. They're supposed to be weak. So let me just call this G. So that means I have a Feynman rule. If you say I have this diagram which has 4 vertex, etc., and you know it has 1/3 factorial in front of it, and it contributes to 2-point process. I say, oh, you know, in zero-dimensional theory, this is 1, this is 1, this is 1, 1, 1, and this is G, G. So in zero-dimensional theory, this thing has a value 1/3 factorial G square. And now suppose you have 7 diagrams contributing to your order. What will happen is the only thing that will matter is how many vertices are, and you'll be summing their symmetry weight. So you will have a rule that says, you know, when I look at this diagram, you know, that one will have a weight 1/2 squared for these two guys. Two coupling constant. And what will happen is when I look at the process, let's make it connected for, you know, something going in, something going out, I'll get that this is 1 plus, you know, there is maybe only one correction or something, 1/2 times G, and so on. And now, with these numbers here, they're just sum of symmetry weight for your diagrams. And if you start doing a perturbative calculation, and if you miss a diagram, you'll discover that you have a wrong sum. So you have to do this. You know, you have to count the diagrams whenever you're doing perturbative calculation. That's the first thing you have to do, just to make sure you got everybody. And it gets complicated very soon because, you know, I'm doing, yes? Well, depends on the theory, right? So, you know, this guy contributes with G, and he has factor 1/2. Well, I sum up them order by order in G. So I convert my partition sum into sum of coefficients times G, and each coefficient is the sum over these pictures that we have, weighted very simply. So in particular, I gave you a very nice example. When you have a directed line, you know, this is called electron. We'll compute it. And then you have a photon. So, you know, electron or positon, and photon. And the first correction to a propagator is this diagram, and it, you know, it has no symmetry, so its value is 1. So it turns out when you do this for QED, the numbers you'll be generating actually numbers of diagrams. And you know, by the time you do this to the 10th order, which is what people have done so far, there is 1,237 diagrams, and you can have computers generating for them. But you know, when you look at them, you can't possibly figure it out. Only for 3 loops, it's 720 diagrams. Yeah. It just gets out of the hand. So you must count them first. And that's one thing anybody can do. That's what these little problems are. Dyson-Schwinger equations still work. The diagrams are still diagrams, but you don't have to sum over everything because everything has value 1 over or coupling constant. So that's why I'm giving you these problems, because this is the last time you can do anything without working very hard. You know, these guys are easy to do, but by the time we start computing, even propagators on a lattice, you know, you have to go in complex plane, do counter integrals, this and that. So there are no cheap things to do in field theory, but this is one. So that's why I'm giving it.